You're going to listen? Okay. Oh, it is. It's on there.
I can just show up. It's gonna be a surprise for everyone.
No, I think that's the piece. We gotta do this right every time.
Apologies for the.
No, it's fine.
Tater asks by far the most brutal questions of anyone here. Sometimes he just rolls around in his fury.
Same.
Okay, it's probably about time to get started. So today I'm very happy to introduce Chris Starnick. Chris is originally from Poland. He did his PhD in Princeton, did a Hubble Fellowship at the Harvard Smithsonian Center for Astrophysics, and a professor at Harvard, and now a professor at Ohio State University. And he has received many awards, and
Too many.
including the Guggenheim Fellowship and the Beatrice M. Tinsley Prize, Fellowship of the American Association for the Advancement of Science, CFA Postdoctoral Fellowship, Polish Astronomical Society Young Astronomer Award, and
Yeah, that was many years ago.
and in addition to all that, he's also brought along some swag.
Yes, but you have to stay for the talk, so I'm sorry. But
So today he's going to be talking about ASAS-SN. So please.
Thank you.
away.
It's great to be here, and at some point I will show the map of the globe with where our telescopes are. But next time, of course, I will take a picture of that and use it. This is super impressive. So I assume nobody here knows anything about ASAS-SN, so that will be my talk. But of course, I understand that some of you might have heard about it before. And so the basic idea is that if you deploy telescopes around the globe and observe the sky, many things happen, and over the last 10 years we've been doing that with huge help with crucial help and from here. And I just want to talk about what we have found. I cannot really cover a lot of topics we have done, but I will just try to give a broad overview. The good news, a lot of young people will be very happy to come here and give talks about any specific subject, so I will mention some names during my talk. The short version of my abstract is that there is this famous American philosopher, Yogi Berra, now deceased, but he said many wise things over the years. And one of them is you can observe a lot of just by watching. And I think, again, we agree here with the crowd here that that's how you make discoveries. You need to take some data, and then you have to have your eyes open. So until very recently, if you talk to people who are not professional astronomers, and even some professional astronomers, people assume that we are actually observing the whole sky all the time. And it just wasn't the case until ASAS-SN, and then more recently a project called Atlas were doing that. And the simple reason why this wasn't done in optical light, it has been done in X-rays and gamma rays and other wavelengths, but in optical light, if you want to do it with decent enough resolution and decent enough depth, the sky is very big. This will be on the exam. How big is the sky, you ask? It's 4 pi steradians. What's that mean? Well, a steradian is a radian times radian, and if you do the math, you arrive at the number of 41,000 square degrees. And if you want to cover the sky with 1 arcsecond resolution, suddenly you are arriving at the number, which is 1 terabyte per epoch, if you want a 1 arcsecond resolution. That used to be a terrifying amount of data. My first postdoc, 1996, and again, I'm very old, I paid $2,000 for 9 gigabyte disk. Things have improved by a factor of, I believe, 1 million. But anyway, it's still, a terabyte. But if you want more than 1 epoch, still a petabyte of data, especially if you want to keep it on disks and spinning, it's still a significant amount of data. And we have arrived at that number with ASAS-SN at this point. And so our approach, part of that is that we have much bigger pixels. We have 8 arcsecond pixels, and that reduces your data rate by a factor of 64, so that helps. But that, as I described, that comes with some cost. But we were able to learn how to deal with that aspect of the project. So the approach is quite straightforward. We want to monitor the sky, 3/4 of it. 1/4 is always behind the sun, but the 3/4 of the sky that you can observe, we want to observe every night. If we use the hardware that we are using, you're able to go to G of 18 magnitude. We used to use V-band filters, but that was just simply because we didn't think about it. Once we thought about it and observed the sky for a few years, we switched to G-band, and exactly the same hardware we gain the magnitude. So it's actually important often to think about what you want to do, but we didn't think about it early on. Since the group at OSU who does that, we don't know how to build instruments. We have people at OSU who know how to build instruments, but the people who are doing this project, we don't. We just bought the lenses and the CCDs. There's some crucial aspect which I will mention a number of times. You also need to find people who actually know what to do with these lenses and CCDs. And again, there are people in this room. And the original idea was motivated by something that we have learned almost 20 years ago, is that some kinds of supernovae do not explode in some kinds of galaxies. For example, superluminous supernovae, by now we understand, mostly explode in low metallicity galaxies. So by the time we started working on this project, we realized that if you really want to have an unbiased survey, and every survey will have some kind of bias, you want to observe the sky. You don't want to observe galaxies where you point the telescope at them, but you want to observe the sky and find things in the sky. So that was the original idea. That's why we have supernova in the name. As you will see, a lot of science we have done, this actually has nothing to do with supernovae. Then another thing that we always wanted to do and are doing more and more is to, once you take all these data, you want to make these data public, ideally with no strings attached, so other people can just grab your data and use it and write papers, and hopefully we're all happy. And so we are doing that, and just 2 weeks ago we have released yet another very good way, I will talk more about it, called Sky Patrol 2.0, where we pre-compute 100 million light curves and update them on nightly basis and release them to people. And that's a very fresh way to release data to the public. Point number one is, if you want to do this, you need to find somebody who actually knows how to do this. And again, this is Las Cumbres, spoiler alert, this is this institution that built these telescopes, deployed them, made them work. We always talk to each other throughout this process. But this is when I talked to Wayne Rosling. We don't actually remember exactly how this all happened, but I think at some point Chris Kochanek, who is my collaborator in this project, visited here, I think 2009, and they got to talk to each other. And we deployed the first telescope in 2011, and then it took 2 years for us to even be able to actually reduce the data in real time. So it didn't just happen overnight. So as I mentioned, we grew over the years. We started originally. Anyway, I'm the standard guy. Kochanek is also a professor at SU. So we started together, and then Ben Shapi, who is a professor now at the University of Hawaii, was a very brave graduate student who said, yeah, I can make this work, and spent the next 2 years writing software and making it work, but of course writing other papers as well. It did work out for him. He was a Hubble Fellow, and then now he's a tenured professor at Hawaii. So in that sense, I couldn't guarantee that this would happen, but nevertheless, I was happy to see that this happened. All the people in yellow at some point were either are at OSU now or used to be at OSU. So the other part of the success of our project is that if we have a very good graduate students, we just never let them go. No, I mean, obviously they don't have to continue working with us, but we have tried to create an environment where people do want to work with us even after they leave OSU. So various people are either graduate students or postdocs at OSU. And then a lot of funding. Is this? Yes. Okay, well, you can't really do this, but a lot of funding, a big expansion of the project came from funding from private foundation, more foundation, and then the Sloan Foundation is currently paying for the operation costs. So I will talk about it a little bit more. You might have noticed one logo missing, but no, it's not missing. There's a really, really big contribution from this institution, and I'm just saying that because I'm here. It really is just that simple. We could not do this without you. So thank you again, and we make sure we always thank you in every single publication which we do. So what do we do? We have these commercial lenses, beautiful Nikon lenses. They all would always come to my office in these beautiful boxes, and I would unpack them and inspect. And these were 10K a piece, and then we have 20 of these, and then we bought 20 CCD cameras. These are 40,000 each. So that was total hardware cost just to buy that hardware, not counting the mounts and other hardware. It was $1 million for the project. And if you translate this into the sky, this gives you 4.5 square degrees on the sky each. And so we have 4 of each per mount. Here's one of the mounts. This is in Hawaii. And once we switch to the G-band filter, it turns out the sky is just fainter and transients are generally bluer. So that allowed us to go magnitude deeper in exactly the same exposure. And that was a big step. So originally we would go to V of 17, but once we switch to G-band, we can go to G of 18 magnitude. And using these 20 telescopes, when the weather is clear at all places, which doesn't happen all the time, but does happen actually, we can obtain 6,000 science images. So if you then multiply 4.5 times 6,000 and divide by 3, which is we observe each point on the sky 3 times, you have actually 40,000 square degrees. So that's actually more than enough to observe the 3/4 of the sky that's observable at any given time. And there are nights where literally we have observed the whole sky, 30,000 square degrees, using this setup. So by now we have taken 10 million science images, and each year we add about 2 million science images to that, which are sitting on the disk and are accessible both to us, but now they're also accessible to the broader public. They cannot grab the images, but they can grab various data products. So again, we started in Hawaii, I think it was 2011, with just 2 of them. We then deployed in Chile. We expanded in Hawaii. Then we had 4 in Chile and Hawaii. And then in 2016, we have received a grant from Moore Foundation and some extra money. And we were able and with very quick turnaround, I think 6 months at the time, Las Cumbres was able to deploy these other telescopes. So almost overnight, we went from 8 to 20 and switched to G-band at all of them at the same time. And so that really, that's only when we were able to observe the whole sky every night, basically starting in 2017. I will show these 2, which don't exist, and it will probably never happen, but if we had another $1 million or so, we would make that happen just because that would complete our coverage. But the truth is, it's not super important for what we do, as I will discuss, but it would be nice. So it probably will not happen, but I would I like to imagine that somehow it will happen. We're always greedy. We always want more telescopes. So this is how our images look like. We have, because the lenses have vignetting at the corners and on the edges, Ben Chappie came up with this staggered. So they're always overlapped. So at the edge you get the worst quantum efficiency, but now you have always 2 images when we observe the sky, and in the corner you actually get 3. And so this means that for roughly 20% of the sky, we actually have twice as many images as I will show in the map. So there are some regions of the sky where we have twice as much data. And then this tiny small field of view that's Rubin. That will be the Rubin Observatory. Of course, they will go to 26 magnitude, but nevertheless, they keep bragging about their huge field of view. We do have them beat, and we have 5 of these setups deployed around the globe. The full moon is there as well. So here is our sky coverage as of Monday, and for many historical reasons, but also weather reasons, we have 8 telescopes in Chile, and they can observe to +30. So we started in the north, but by now we actually have better coverage of the southern sky because we do get more data from the south. And so ideally we would somehow balance them, but honestly at this point we don't really care. It's more about, did we get more, we try to optimize the recent data as opposed to global data. So the scheduler by Ben Chappie kind of tries to, it checks how recently was the field observed and then tries to observe this field. It's not checking how many times the field has been observed in the history. But every point on the sky has at least 2,000 images, and some points are approaching 9,000. At some point, something glitched, so there were 2 fields on the sky which were observed 5,000 times each in 1 year, and we have no idea why. And we should probably go and dig in these data, but we just never did. So it's not perfect, but it's good enough. It works. So how does that work? How do you observe the sky with these giant pixels? there's this magical software which I've been using for 20 years, but I'm still amazed that it works so well. It's called image diffraction, and this was the software we write is called is called ASAS, which was written by Christophe Allard, and he actually visited me at CFA because his first version just didn't work, and so I invited him over many years ago now to come and work with real data and actually make it work, and he came and he made it work, and then we adapted it to ASAS-SN. So you take a bunch of images, try to point exactly at the same spot. You can never point exactly at the same spot, but again, with your mouse, we can point very closely to the same spot. So you take a bunch of images, you combine them, you register them on the same grid, and then you make a deeper reference image. Again, many of you have used image diffraction, but just to explain that this is Large Magellanic Cloud, of course. Then we take a new image, which is just slightly offset. So we bring them to the same grid, and then we match the photometric 0 point, we match the PSFs, and we subtract them. That's one of the tools that I brought to this project, is that really how you make this work. And now you do this over and over again. So this way the galaxy goes away, and all you deal with is that sources that varied, both sources that became brighter, but also sources that became fainter. And now you, instead of measuring brightness of every single source, you're only finding sources that showed up at any given night. The way our pipeline is built, we actually don't ask that source if it was there last night, at least when we detect it. We just ask, is there a new source in this image? Or more correctly, in free images, because that's why we take free images, because otherwise you get swarmed by artifacts. So that works. So then the next step is we have 2 million transients per night, which of course we cannot really, most of them are just, the technical term is crap. And so we have to deal with that. And again, we have learned, we don't really tweak this anymore, but we have spent several years tweaking our pipeline to deal with it. And then we make many cuts. We have 2 different machine learning classifiers, which are at this point several years old, so we could probably do much better. But then, because our project is still relatively small in terms of number of discoveries, because we don't go that deep, at some point a human, and that's unfortunately, or fortunately, it's just been me for the last 10 years, looks at JPEGs. And I do this every day, even when I am on vacation. And I look, it used to be more like 500, but now it's more like 100 JPEGs. And then, so we at no point yet, we do not issue automated alerts. There's always a human verification. I'm still mostly human, even after we're looking at million JPEGs in the last 10 years. And so here's one JPEG. Again, I cannot shine the laser pointer, but here, if you squint, there's a source, there's a circle. It's always at the center, so that helps. And this turns out is the most luminous supernova ever discovered. At least we think it was a supernova, ASAS-SN 15 LH, which in this didn't look very impressive, but of course, luminous doesn't have to be bright. It's just it was basically borderline detection of our project. But once we took spectra and did the follow-up, we convinced ourselves this was a very interesting object. So most of the detections will always be at the threshold of detectability, because that's how astronomy works. But occasionally, something like this shows up. That's at least a 3 sigma detection right there. And that's a joke. And so that's a galactic nova. So some objects are just very easy to discover. There's only a handful of these per year. Well, maybe 20. Actually, a lot of work. We did a lot of work, which I will not even discuss, with our collaborators at Michigan State. And they had a beautiful thesis. Adam Kawash wrote a beautiful thesis on galactic novae. It turns out that we actually were able to change that field quite a bit. I don't even actually talk about it, but there are many different things to do. So once we find something, the big part of my job, the reason I still do this, and we didn't give it to we have research assistants and graduate students, but honestly, I don't trust them, because I have developed by now a lot of judgment about what to do next. So it's like, if I see this, I email people and it will post an ATL. If I see this other thing, then I maybe do. Well, we always use TNS as well. TNS didn't exist when we get started, so that was relatively new. We used to send a lot of ATLs, but we don't do that anymore as much, because it's just, there's no need. So follow-up has been a crucial part of this project, and there we have our own telescopes. Ben Shappi is in Hawaii now, so of course they have telescopes. Traditionally, a lot of our graduate students, several of our graduate students went to Carnegie, so we use Magellan quite a bit. We have used Las Cumbres facilities a lot. the two crucial satellites for us, it turns out, were not the big ones, were actually the small ones, Swift, which many people here use. Swift is just wonderful because we are about match in terms of depth. So anything we discover will be observable by Swift. And ability to get quick UV data was just wonderful. And TESS, as I will mention, TESS doesn't follow up, but we did the reverse. We follow up TESS, and we pre-discover TESS objects because they have a gap in downloading data. So that was a very clever thing, which again Ben Shappi came up with, that we will focus more on TESS fields so we can actually find something and trigger follow-up observations before even TESS data are downloaded on the ground. And so and we had beautiful collaboration with many, who I call unpaid professional astronomers, amateur astronomers who have bigger telescopes than we do. So in that terms, they can do follow-up of our discoveries. By the way, I should say, if you have any questions, just interrupt me at any time because I tend to talk too much. So I remember as I was preparing this talk that our first announcement of real-time discovery was 10 years ago. I'm on my sabbatical here now at KATP, but I was on my previous sabbatical in Hawaii, and I was trying to get some beach time there, and my collaborators were yelling at me that I should be working, but anyway, we were just figuring out how to do things. For example, there's this thing called asteroids, which provide many true transients every night, and they move. So we figured that out. And once we figured it out, we discovered some CVs. Our first supernova didn't happen until June. But in the meantime, we were starting discovering cataclysmic variables. And it turns out we're basically discovering one new CV every day. So we have discovered by now 3,000 of them. But early on, we just didn't really know. I mean, we knew what's out there, but we didn't really appreciate what will be the things that we're discovering. So that's our very first real-time announcement. It's not the very first ASAS-SN publication because we took some data in 2011. But this is the first time that we have found something in real time. And even then, we were kind of delayed by a few weeks because we were still figuring out how to communicate these things. And that, of course, has a number of people from here listed. So I will talk about science as well. But so we have a science team, which is now, I think, about 40 people at many different places on Earth. And our graduate students, as I mentioned, even when they leave the OSU, they usually collaborate with us. And so at this point, we write roughly 20 papers a year in the team. And that team, again, is in many different places now. Supernovae are still the goal, and we discover them. The ratio of, we have what we call discover when we're the first one to discover it, to find and announce, which is what discover is. And then we have recovery, where we find something that somebody else has already discovered. That has been varying over the years. We used to discover roughly 2/3 of all the bright supernovae in the sky for several years. But both ZTF and Atlas go significantly deeper than we are. And roughly 75% of the supernovae in the magnitude limit sample will be type 1a. So of course, they will see them first. So that's just expected, and actually kind of relief that we don't have to be there, because how many times, I mean, nothing against type 1a supernovae, but it's just, there is extra work in discovery. Recovery is just much simpler for us. So now between discoveries and recoveries, we have detected more than 3,000 supernovae at this point. So it's roughly 300 a year, to going to the magnitude of 80. And we are writing statistical papers. We haven't really focused on that as much. So you can still do statistics. It doesn't matter if you discover them or recover them. And one other reason I still do it, I never look at other people's data when I make a decision, is this a detection or not, because we want to make some consistency in the way that we detect things. Something that wasn't really on our radar, because it really wasn't a thing. People talk about it, but really that science has opened up quite a bit in the last few years, well, 10 years. There's tidal disruption events, which we discovered about, I think it's 11 at this point, and we have recovered or detected another 30. So that has been kind of a surprise. Less so now, but first we found the first one in 2014. And we just didn't even know much about what these things are, but we became quickly attuned to the fact that they happen. It turns out when you observe the whole sky all the time, you find variable stars, even at bright magnitudes, and especially because of the cadence. So we actually discovered roughly 350,000 variable stars, new discoveries. And also an important paper that we wrote many years ago, 2018, is where we used our data to characterized known variable stars, turns out many thousands of them had the wrong classification because it just was based on very partial data. So because we have thousands of data points by now, we can look in a uniform way at variable stars and actually make important work there. Cataclysmic variables, one a day. There's lots of white dwarfs with companions, turns out, that do things, which I'm not. They're interesting objects, but we never had anybody on our team to do anything about them, but we announced them and other people were working on that. Something that was, again, number of times I mentioned in my talk, we have discovered the biggest or the strongest or the largest amplitude things. And then again, that comes from the fact that if you look at the whole sky, it's actually easier for us to find a giant M-dwarf flare than for other people because it will be bright and it will show up. So we have the biggest M-dwarf flares ever discovered, and I will talk about it a little bit. A big surprise of this project was TDs, and also we have now discovered something that people probably suspected, that accreting black holes are complicated, and they can do, supermassive black holes, they can do weird things. And so there is not just tidal disruption events, but there are objects called ANTs, ambiguous nuclear transients, which I don't think some people in this room probably know more about, but there's still some debates what they actually are. And so there's the traditional AGN, there's TDEs, but also there's some intermediate class of objects which behave neither of these two ways. Classical novae is always been fun because at least they're easy to spot, and they're actually very interesting. We discovered 2 comets, and that's really is weird because our software rejects moving objects. So it's a case where also lots of people are looking for them. So we got basically lucky. One of them really, I think, had some eruption and became brighter very dramatically quicker. So we were finding it, and we found one killer asteroid, which I will mention. That was back in 2018. That was very exciting. The other important aspect of this project is that we think good mentoring is important. There shouldn't be a controversial point, but nevertheless, it's something that we focus on. And so, I mean, very naturally, young people, junior people lead the papers because that's what happens. And so, of the last 20 papers, 17 were led by graduate students or postdocs, and that's just how we do things. But also, it turns out that of the top 10 most cited papers, 8 were led by a graduate student or postdoc at the time. And so we don't, when a really exciting discovery happens, we don't take it away from young people. I'm not saying other people do it, it's just that's how we do it. And so that has the nice effect of that our students were quite successful generally in terms of finding positions, and especially lots of them went with several of them went with Hubble Fellowship to Carnegie. Somehow that became a path, and then they went somewhere else after that. Okay, so let's talk about science. Here's a picture of a zebra. Well, how do we know it's a zebra? Because it looks like a zebra. Where was this picture taken? No. No. You have mountains up there. So the first week we came here, it was raining, but then it stopped raining. So I said, let's go to the mountains. We found some road, and as we were driving on the road, there was a zebra. I'm not making this up. And so there was a zebra, and so we took pictures because we were surprised there's a zebra. And then we came home and we Googled. It turns out that it wasn't just us; other people have seen zebra too. So there's some wild zebras in your. And if you didn't know about it, you should go and see the zebra. I do not guarantee the zebra will be there.
I wasn't sure zebras were real.
Well, we didn't touch it, but it did start following our car when so it was a very friendly zebra. The reason I'm showing it is, first of all, you always have to show something local in the talk because that's a good form. But also part of our project is to find known objects in unusual locations. So that's a zebra. But now if this was a dragon, that would be even more exciting. And I think we have discovered some dragons, but that's easier to convince people that so if I showed you a picture of the dragon, you'll be telling me I just photoshopped it. But this one is real. But we still had to we all saw it, but we still had to go home and Google it just to convince ourselves that it was real. So that's why I'm showing this. So let me start with variable stars. We observed the whole sky. We knew we had very good data, but we focused very much on supernovae and other transients in the first few years. But then a new student showed up, Tarindu Jayasinghe. He was originally from Sri Lanka, and then he was undergrad in California, and he came to SU. I had to convince him that he was worrying about winter, but I convinced him that he will be okay. he's now a Hubble Fellow in Berkeley, so he really left Ohio as quickly as he could, but nevertheless he came to Ohio, and he knew something which I still trying to learn, not really, but at least I'm learning what it can do, which is machine learning. So he said if we use the tools of machine learning and ASAS-SN data, we can actually do a uniform classification of variable stars. So we can extract the light curves of known variable stars, extract light curves of the variable stars we have flagged. As I was clicking through all these JPEGs, I have flagged many thousands of variable stars. So we just didn't do anything with them, but we had the file. And he classified this. And so he wrote this paper with discovery of more than 200,000 variable stars and reclassified and classified another 300,000 known. And this paper has more than 200 citations by now because we also made the data public to other people, the light curves from this. So that was very neat. And then, of course, we did it again with G-band data, and we found another 120,000 variable stars, new variable stars. So again, 18 magnitude is not that bright, but that's still saturation limit of LSST, Rubin, will be 16 or 17. So we are finding really the brightest objects in the sky with thousands of data points. Not surprisingly, many of them are clustered. They form a ring on the sky. I wonder what that would be. And one thing that we not just published the catalogs, but for example, we have found, I think, close to 200,000 eclipsing binaries. And among them, there's 40,000 detached eclipsing binaries. So my only graduate student right now, Dom Rowan, wrote a code that fits, light curve fits them. And if you know anything about fitting eclipsing binary light curves, it's actually a very non-trivial problem. So this is the biggest by far catalog of detached eclipsing binaries with fits to them. And we just started exploring the science of this. And so this is also on the web, include both the data and also the fits. And the awesome thing, which I don't need to convince you, but if you're doing galactic work, the fact that there's this thing called Gaia, which tells you the distance to stars, it's still something that I am used to it by now, but I grew up in Hipparcos era, where Hipparcos was awesome, but that was going to maybe 200 parsecs, and now you can have a distance at 2,000 parsecs. And so when we combine our data with Gaia data, and Gaia is deeper than us, so that's even better. We can do things like that where you actually find something and then you know its distance, so you know its luminosity, and we've been selecting interesting objects for the follow-up studies. And then this was an object discovered by the Macho project in the Large Magellanic Cloud, and they classified this as an eclipsing binary. But once we look at our data, we realized this was what is called a heartbeat star. And then Tarindu, he writes too many papers, which is a good problem to have. He wrote 2 papers about this object. It turns out it's a 30 solar mass star plus 10 solar mass star in a very eccentric orbit. There's probably also a BE activity. Anyway, it's a very interesting object. And usually heartbeat signal is 2%. In this case, you have a 20% heartbeat signal. This is when the star becomes stretched in the close approach and then starts to oscillate as it moves away from the companion. Giant dwarf flares. So our very first ASAS-SN paper, I think, the real time was in 2013 when I was scanning the sky and I found a 9 magnitude brightening of an M dwarf. And we were lucky and we were even able to trigger ASAS-SN to do the follow-up of the same object the same night. So we have that ability, we just don't do it very often. So that's why there is initial data point and there is another data point 2 hours later. And this was a super flare which released enough energy in volumetric energy, equivalent energy of roughly 3 months of the luminosity of the star. My joke is always like, if you see one of those, you probably, your afternoon is not going to be very good, or the next several afternoons. And that, by now we have seen one more, even bigger flare, which was 11 magnitudes of brightening in the U-band. So volumetrically it's not 11 magnitudes, but in the blue bands, because the stars are red, these flares is brightening by a factor of more than 10,000 in some cases. So these are very impressive. Cataclysm variables, that's all I'm going to show. We keep finding them, and if any of you are interested, I mean, they're all public, but we had a collaboration in Japan who has been very much, there's a huge amateur astronomer community observing them. They have a very unusual behavior. They're very interesting. We never, any of us have done any work on that, but we discovered roughly 3,000 of them by now. Novae was great, and this is collaboration with Laura Chomyuk from Michigan State University and her postdocs and graduate students. Here is some situation where we yet again got lucky. We discovered a nova. It's the one with the arrow pointing at it. It's right next to this other bright star, which is this is the Eta Carina region. And this happens, there's a bright nanosatellite was staring at that bright star at the time when we discovered the nova, which gave you the upper light curve. So that's, again, telescope in space, but smaller than ASAS-SN. And then it also happens that Fermi is, of course, observing the whole sky, and they were able to correlate the gamma ray data with optical data, and they were showing, and this was a Nature paper, so I couldn't be on it. I had to take myself off, but nevertheless, very interesting paper. I have a rule. I have no Nature papers, but well, it's just a random thing. But we all allow a quirk or two, and they showed basically that the novae, which we always thought we understand, we don't understand novae. It turns out that it's not just nuclear runaway on the surface of a white dwarf. Yes, there's that, but there are also shocks with the companion. So anytime you see gamma rays, you also see corresponding peak in the optical light. That's all I'm going to say about novae, but there's a number of papers written with ASAS-SN discoveries. And again, we were able to provide all sky coverage, which is actually so the very nice paper of Adam Kawash are about rates of novae and comparing rates of novae in Milky Way to Andromeda, which is it's actually easier to find them in Andromeda because you just point in one galaxy and they're bright enough to actually be seen. In our galaxy, you sometimes look for dust. There was always a question how many of them we miss because of dust, but he showed that we maybe miss 1/3, but we don't miss factors of several. Okay, so we do observe supernovae. We discover them, we write papers about them. Probably not as many as we thought we would, but there's some interesting cases. This is artist's conception of the most luminous or most powerful supernova ever discovered, ASAS-SN 15LH. And so we had a big press release, and we had the science paper. So yeah, I have nothing against publishing in science. We had the science paper again, and it is definitely very luminous. The redshift was kind of hard to measure, but multiple. We all agreed the redshift was 0.2. Once you know the redshift and the brightness, you can convert to luminosity, and so that's the upper light curve. And you're comparing to this is the comparison you will see often. And it was even more luminous than the most luminous supernovae. And it was a factor of 1,000 more luminous than 87A. It's a factor of 100 more luminous than the typical 1A supernova. And it lasted for months. It had the second peak. We had beautiful Swift data. We still think it's a supernova. There were some papers claiming it's a TDE. The truth is that he thinks that's the case. He is wrong, but the important thing is that nobody has found another one since. And I fully expected that if we found one with these tiny little telescopes, ZTEF would have 10 by now, because if you do the math, they're easily seen up to redshift 1, and the volume does grow like a cube. To my knowledge, I don't know if that's true, but there are other superluminous supernovae, but nobody has found an analog of this since 2015, which is worrisome. Now, this object is real. We're not the only ones observe it. We observe it with multiple satellites. So the fact that nobody, even if it's the TDE, still the other TDEs don't look like this one. And so on, tidal disruption event. Anyway, challenges all the models. There's another case where we got lucky, where Kepler is no longer with us, but Kepler had this one of the ideas. Kepler would read stamps, and some of the stamps were placed on galaxies. And so we observed the sky as well, and we discovered the supernova, which would have been discovered by other people because they were also looked, but in this case we actually were the first to point at it. And it became the supernova I think it's still the case, with the best light curve ever in terms of precision. So you have the data from Kepler, which is that really the thing that looks like a model, and then there's other data from our project. I'm not going to say much more about it, but there are several papers written about this object. Just an example of if you're observing the sky all the time, you will keep getting lucky just because you help the luck. So this gave us the idea. We had George Ricker give a talk about TESS. Before TESS was even a satellite, so maybe that's 2012. And he mentioned this idea for this satellite, which in some ways is quite similar to ASAS-SN. even smaller telescopes, bigger field of view. They don't scan the sky, but they will stare at roughly 1/24 of the sky at any given time. So it's a large number of square degrees, more than 1,000 square degrees. But they have this weird orbit where they go out to the moon and then they come back. And they can only download the data every 2 weeks. So we had this good idea, I think, is that when we know where the test is pointing, and we know where the test is pointing in the given time, we will take more data at that time with ASAS-SN, reduce it, and then if we discover something, we will announce it as well and take spectra and so on. So that worked number of times so one thing we learned, we had a very good student, Patrick Valelli, who has left astronomy for industry, but his thesis was to learn how to reduce test data, which is 26 arcsecond pixels, so even much bigger pixels than ours using ASAS-SN pipeline. And there's as always, you have to learn some tricks, and there's some new tricks. So that worked quite well. Test is much smaller, so the light curves are not nearly as good, but we had some good discoveries here as well. Another thing that we started being interested in, and we don't really have a lot of discoveries because it turns out these black holes that don't interact are actually there's probably lots of them, but most of the time they're hard to see because there's a black hole next to a star. And if we had the radial velocities of all the objects in the universe, that would make it be easier, but that's not what we have. We have light curves of things. That helps. And so there is this plot which you must have seen by now. Here the black holes from LIGO. The x-axis has no meaning here, but the y-axis has you look at the merging black holes, so you take two of them and make a new black hole. So as they always say, we have observed 3 black holes, 2 before and one after for each of these events. And here the neutron stars, and then here EM black holes, which are black holes, all of them are interacting, namely there's a black hole accreting from the companion. So that's almost certainly is a biased sample in the sense that somehow we are just seeing the cases where there's 2 stars still close to each other. And that, I think, total number of these objects is around 50. And there's maybe one new one discovered every year because we already discovered the obvious ones like Cygnus X3 was discovered. The first time they sent a X-ray satellite into space, they have seen it because it was such a conspicuous source. So the new sources are usually discovered where the black hole is quiescent and then has an episode, and then we discover. So we, for example, discovered one in 2017 in optical before it became an X-ray source. And I'm trying to say we actually have at least one case of non-interacting black hole where ASAS-SN was part of the discovery, but we hope to discover more. And one of the avenues to do that is that if you have a companion star close enough but not donating material, it will become distorted by the gravity of the black hole, and you have ellipsoidal variation. So Dom Rowan is the same person who did the work on the eclipsing binaries. His very first paper at OSU was to grab basically a lot of our variable stars and then do the fits and look for ellipsoidal variation, and also use test data in this case as well. So these are all relatively bright objects. We have not yet found any black holes this way, but it's part of the process of looking for them. And then something that has been very rewarding. How am I doing with time?
About 15 minutes.
Okay, I will speed up. So supermassive black holes are super awesome. We have them as well. So the big discovery was TDEs. It wasn't our discovery. Other people have seen TDEs. What is again good about the ASAS-SN that if we discover a TDE, is going to be a bright one, and usually a nearby one. And to our surprise, we already had, I think, 2 in 2014, and then we had 1 in 2015. So it turns out that because we used to be very good about the COVID didn't help with this, but we used to basically take a spectrum of every single supernova candidate, either us or other people, including people here. So our spectroscopic completeness was 90%. And that included objects at the very cores of galaxies, where in the past, some supernovae surveys would actually avoid the course of galaxies, but there's interesting stuff in there. And once people started taking spectra, it turns out our TDE rate was roughly 1 in 80 type 1a supernovae compared to, let's say, 1 in 500 for other surveys. So the fact that we had this high spectroscopic completeness allowed us to discover more TDEs. So what is the TDE? The star comes in, something disturbs its orbit, comes close to the black hole, and in most of the TDEs, there will be just one-time encounter. where it will become disrupted, but that the stream from the TDE, so that's why you have this picture here, intersects each other. And there's a complicated physics that I'm not ready to describe, but there's going to be a TDE workshop here at the KATP next year that I am actually thinking about going to, but nevertheless, there is a lot of activity. What actually happens when TDE happens? For me, as the person who is looking at the JPEGs, I'm like, oh, there's something happening in the core of the galaxy. We should definitely take a spectrum, especially if it looks like it could be a TDE. I usually cannot tell early on because, unfortunately, TDEs and type 1As basically do the same thing. They get brighter, and so you really have to take a spectrum. Once you have a spectrum, they're really easy to tell apart. And so here is a lot of work done by Jason Hinkle and then Tom Holloin, who was a graduate student at OSU as well. Jason Hinkle is at Hawaii. And here's the sample with well-observed TDEs with Swift, which you do need because it turns out they're so hot, the temperature is 30 or 40,000 kelvins, that if you actually want to understand the luminosity of a TDE, you have to have UV data. So again, that it helps that our sources are so bright. And then the sample grew quite a bit in the last few years because more TDEs have been discovered also by other projects and then quickly observed with Swift. And there are people working on TDEs here. So again, we got lucky that one of the TDEs we have discovered, ASAS-SN BT, not TB, somehow either is BT or TB, but this was 19 BT. It was discovered in the test footprint, and better yet, it was a test continuous viewing zone. So there's a beautiful test data for it. From that point of view, there have been other TDEs with test data, but this one is unique. That's just sitting right there in the southern continuous viewing zone. So as you can see, there's our data on the left, test pixels even bigger, and then follow-up data with Las Cumbres telescope. It's right in the core, and of course, then you take spectra and observe it. And here's the light curve. Here's the light curve from TESS, and here's multi-band data from us and other observatories, including Las Cumbres and also from Swift. So again, that's a talk in itself, and if I wouldn't be giving this talk, but there are people in the collaboration who will be happy to give a talk about this. And this is probably the most interesting transients that we have discovered. And I'm not ashamed to say it, that I found it's called 14KO because I found it back in 2014. We even took a spectrum and we just failed to understand what it was. We just announced it the supernova and we forgot about it. Because we are not perfect, close, but we're working on it, but we're not perfect. I'm joking. So what happened, Anna Payne, who is again Ben Shapi's graduate student, was using ASAS-SN data to look at AGN. And so but we didn't want to be biased, so she just took light curves of a whole bunch of centers of galaxies on the sky, because we have these data. And she was visually looking at them. It turns out that I've done that, not just JPEGs. You can look at 5,000 light curves in a day, no sweat. That's just like, but you have to get automated. And the eye is amazing about seeing things like that, especially when you're seeing is one of these light curves is periodic. So ASAS-SN 14KO, when we found it, was just one of the many, by now 30 outbursts of a periodic TDE. It has a spectra that look like a TDE, but it comes back 120 days later as another episode. So some TDEs, small fraction of them, most likely what happens, the star gets disrupted, but just a little bit, if it's an eccentric orbit, and then get disrupted again, and disrupted again, and disrupted again. So each time we think it loses about Jupiter mass, which then becomes accreted, and it's a TDE. Why is this great? Well, first of all, now you can predict a TDE. So Anna and Ben have been successfully obtained Chandra time and HST time, JWST not yet, but it's not obvious we need it, but Chandra especially because there's some complicated X-ray behavior. And you can, they don't like target of opportunity observations because they disrupt their schedule, but if you tell them this is when it's going to happen, they like it more. So we've been quite successful in getting time for this object. And so there's several papers written by Anna she's graduating, she's going to be at JPL. So if you wanted to hear a talk about this, she's just down the road. Well, 2 hours, but well, 4 hours because traffic. But. And here's some more data. We have observed in V-band and G-band and then in TESS again, so we had some test data for it. And once you look closely at the data, it turns out there is this classical thing called O minus C, observed minus calculated. The period is becoming shorter. So as the star is losing mass, something is happening. Well, it's our scenario. It's more, I've actually theorists agree that because there's nothing else that works. So this basically this partial tidal disruption event works very well. So this was in the original paper by Anna in 2020, and as we acquired more data, it actually became even better. So we can calculate this O minus C quite well. So you're already asking this question, but because you're shy, you're not asking the question aloud. This cannot possibly last forever. At some point, this star will say, "Come on, enough." So we think it might be happening. In the last time, instead of just having one peak, it had two peaks. Well, we're astronomers, so that's significant. We're not yet saying the doom is impending, but it's definitely interesting that it had. But even then, not every peak looks exactly the same. But now, in the very last, this was updated. I think I asked Anna on Monday to update this, and so this is the last peak, and the new peak is just about to get started. So yes, of course.
If you're also saying that the period is decreasing, can it be predicted how much longer?
Well, but we don't have. I think if you ask theorists, maybe there's a new paper by Brian Metzger and a graduate student. I think I haven't kept up with the literature as much as I should, but there's a lot of literature. So that's why this is really just kind of whet your appetite talk. And so if you can grab some of these people to give a better talk, that would be good. But that's up to you.
What's the absolute magnitude of those peaks?
Oh, how bright this thing is? It was 16.
16 apparent?
16 apparent magnitude. Oh, absolutely. This is basically it's twice as, so it's Milky Way luminosity. But I could get you a better answer. I just don't want to make up the answer. So okay, I will skip this. This is actually very interesting work, but we also use this paper as a survey paper. So this is a very well-cited paper. We're cheating a little bit. We've just like everybody, we have a gravitational wave trigger. We haven't seen anything, but if we did, you would probably hear about it. But Ben Shapi is again getting ready with graduate students to do that. I'm too old, so I just told them, don't wake me up. I used to do work on GRBs, but that was 20 years ago. We also do trigger on neutrinos, and neutrinos connections are always tricky, but we were part of their big NSF press release a few years ago because we had data, and it turns out that we have seen a blazar behaving badly. Now, blazars do behave badly often, so it's not. I think this neutrino association, most of people do believe it, but nevertheless, our data were not crucial, but they were part of the story. All right. No. Somebody has to do something.
Just restart the slideshow.
Well, I could finish here, but that's a sign.
Here we go. I think we're back in business.
I think it was a zebra.
It's the zebra. Yeah.
Which one? Oops. Which we restarted from?
I can just start a new one.
Okay.
All right. We go back a little bit. Yeah, so there was a comet that was fun, and then there was this asteroid 2019 OK, which we found, and I had to steal Las Cumbres observatory code because we don't have a code to submit observations, so I apologize for that, but it was emergency. And it turns out later the same day was passing by Earth at 40,000 kilometers, and everybody was excited, and NASA was upset that somehow we didn't tell them. But anyway, it was interesting, but that's a different story. So now, what can you do for us? Of course, you've done plenty, but what can we do for you is that we have a lot of data, which is public and it's sitting there, and we love when people use it because it makes us feel good, but also we tell funding agencies that people use it, and so that's everybody's happy. And so, for example, we have the Sky Patrol, that if you found something new on the sky, you can just go and type the coordinates by hand or by using a mouse. It's not automated. And it will calculate the light curve for you. it takes a few minutes, and you will have a light curve, and you can do whatever you want with it. Just give us credit that you gave our light curve. So that's called Sky Patrol, and it's been very, very popular with community because now you don't have to observe your star every night. You can just grab the data from us. Here's the collapsing binary catalog. The newest thing is the Sky Patrol 2.0, where we pre-calculate 100 million light curves and then update them nightly. It turns out it's a very complicated thing to do. So Ben Shapi, again, I mentioned him many times, and his graduate student took about 2 years longer than expected, but since I have no idea how to do it, that's how long it took. And now it's been deployed 2 weeks ago, and apparently they already had close to 1 million light curves downloaded. Just because they're pre-computed and it's very quick. Now you can download 10,000 light curves at a time as opposed to calculate one at a time. So we suspect this Sky Patrol will be used a lot by people just because it's very convenient. There'll be still times where your object is not in their database and you want to use the previous Sky Patrol, but most of the time you'll be happy with this. We have done a citizen science project. This is again Tarindo Jessinger. He's actually Hubble Fellow at Berkeley, so if you want to hear about variable stars and black holes, stellar black holes, he works on that. And so this has been fun, and I still very much interact with them, not daily, but I answer questions and so on. So this is fun. And it turns out citizen scientists, 5,000 of them looked at 1.5 million light curves at this point. Slow down as always, but we already wrote one paper and we'll write more. There's the paper. All right. I grew up in communism. If some of you don't know what it is, I'm happy to explain later. It will be a short version, but the one thing we learned in communism is that it's good to have a 5-year plan, but if you can read Russian, the best 5-year plan can be done in 4. So what is our 4-year plan? 4-year plan is that we will keep running because we think it's a good idea. And we are also funded to run until 2026, and this is paid by Moore Foundation and Sloan Foundation. So in 2017, Moore Foundation paid for more telescopes and the operational costs. And then now we are funded by private foundations until 2026. So it's still 2023. So I don't have to write proposals right now, but basically next year I will start talking to them if they will continue funding us. Why should they do that? Well, there is no perfect way to measure impact, but citations, people poo-poo citations are very important and they're actually very useful because we, as well-behaved scientists, when we use somebody's data, we generally cite them because if somebody gives me data, I will cite them and thank them. And so our survey paper is, as you can see, still being cited more and more. That's good. We haven't peaked. Maybe we'll peak, but so far 2023 looks good. The way I look at it is we thought it was worth running back in 2017, and now we have 3 times as many citations per year than in 2017. Now, there is not an objective measure, but nevertheless, we are still very much, our impact grows faster than linear. So our cost is more or less linear, although there's inflation. Our impact is definitely faster than linear. Maybe it's not quadratic, but it's faster than linear. And then the paper below is the original Sky Patrol, which is the simple Sky Patrol where you ask for light curves. And this one has served 400,000 light curves, which is not a lot, but remember, these have to be done by hand one at a time. So that's actually a lot. And in some ways, of the 400,000 light curves, there's only 750 papers, but we'll stay take. Both of these papers are in 0.1% of most cited papers in any given year in astronomy. Usually the top few is like Planck or cosmology will take and of course 2017 the most cited papers are gravitational waves and for good reason. So, but we're doing extremely well in terms of our impact and that's one of the reasons I think we should keep going. Okay, we don't need to restart. I also have a slide comparing to other transient projects, and our impact is as large as Zwicky. Our impact per dollar is harder to quantify, but I think we are roughly 10 times less expensive in terms of yearly cost. But I don't exactly know how much they're paying. I know roughly how much we have to have, how much money we have to run. So from that point of view, it's probably worth running. And what else do they have there? Yes, that's our 4-year plan. We have funding for the next 3 years, and then I think it's okay. and then I think we will keep running. Maybe by 2026 we'll change our mind, but at this point there's no good reason to stop. The new Sky Patrol, we definitely want to see how much impact that will have. But the old Sky Patrol was still climbing, and it's not quadratic, but it's still definitely more. As more people learn about it, they're using it more and more. And I think that's all I had. Thank you. And I all right. I have swag, of course. Questions?
I was wondering if there is any plan to cross-match the ASAS-SN photometry catalogue with the Rubin first data release, because you overlap very nicely.
We have some ideas. It's just the last time I looked, Rubin was delayed again.
Yeah.
No, I'm not. This is not a criticism. This is a huge. It's just part of my sabbatical. So I'm on sabbatical here. Was justification was that we will deal with LIGO, which I've been talking to Shapi, mostly he's doing that, and it was how we are going to prepare for Rubin. I think we can do the same thing we did for TESS, observationally, which is where if we know where Rubin is observing, we can actually take higher cadence data. It sounds funny that we would like to compete with using 14 centimeter telescopes, but if they find something very bright, before it's bright, we may actually have the light curve before Rubin comes back. So this would be part of the strategy.
Well, what I was thinking of actually is because the magnitude range complement one another so nicely, anything that's bright enough to really follow up with, say, spectroscopy, for example, is probably going to saturate Rubin fairly quickly.
Sure.
At which point, ASAS-SN coming in.
Yeah, and the Sky Patrol data is public, so you can just grab it and. This one, I think we update within 24 hours because we need to download the data and then reduce the data. But it's still, so it's not instantaneous, but it's relatively quick.
Thank you.
Where are you at on your rates papers? Like especially, supernova rates are a pretty abysmal affair, but you have enough data to do it right.
We have a 1A paper which was supposed to be done last year. What happened is that the person that worked on it was a research assistant at OSU and now is a graduate student working in a different project somewhere else. So the truth is, as often happens, I think he still wants to get it done, but also, so the 1A rate, if I remember correctly, our error bar is smaller, our number is not different from 1As. The type 2 is tricky, as you know, because type 1As are well-behaved beasts and we have more of them. So type 2s we have started working on, but we didn't have a paper. There wasn't anything close to because basically the sample is smaller and they're harder to model.
It's true, but on the other hand, the last decent core collapse rate paper was like 15 years ago, so there's lots of room for.
Oh, I agree with you. It's just, as always, is basically it boils down: is there a person who's going to do it? And right now there isn't one, and it's just, and it's very amazing how good people immediately saturate because it's just like if you have somebody who's good, they're immediately saturated. It's should be a law against it, but there isn't.
What's your legacy? So you say maybe 26, you're ready to continue operating, but what's your data legacy plan?
Well, all the disks we own because part of our proposals. So the data sits on disks that we paid for. So OSU very much likes us and does things for us for free. Well, for free. I mean, we're part of the organization. They get the fame aspect of it. So we had a lot of support from our college. So the plan is we'll just keep it. Even if we stop taking data, the data will sit on disk and be served to people. So that's kind of sounds vague, but that's the level of. That's about the plans we have. We will continue serving data because basically there's no cost. We have paid for the hardware and it sits there. We have just updated the servers. So part of these large proposals, well, large. It's basically $3 million from Moore Foundation and Sun Foundation combined for 5 years. So it's not a lot of money in some ways, but it's a significant amount of money. NSF kind of falls in the gap of NSF. So it's an MSIP level proposal, but we were not successful with MSIP. That's a different story. Anyway, so we don't use at some point we were thinking about Amazon Cloud and stuff like that, but of course these are exactly where you have to pay and keep paying, and so we went to let's buy our own hardware and do it. We started talking to Space Telescope, and first of all, I was surprised to learn that ASAS-SN has collected significantly more data than Hubble by now, in terms of Hubble just doesn't. They take longer exposures. They have lots of images, but our data is significantly bigger than TESS as well.
But Penn-STARRS puts theirs to mass, right?
Yeah. So, but basically, the MAS told us unless we have a way to pay them, they're not going to do anything for us because they don't have money for that neither. So so we would have to come up with a way for them to host the data somehow, which we would like to do, but they said, well, it kind of again falls between Josh Peak, they don't have money for it. NSF is supposed to talk to NASA, but there is no actual funding mechanism for this. And as again, astronomers kind of are left to, I'm not surprised, but nevertheless there is. So the answer is we are committed because we think it's a good idea to just keep the data coming. But we do want to run for at least 5 more years after that. If there's real clear sign that we shouldn't be running anymore, I don't know if people will just stop using our data completely. I don't know what we will be. Nobody else is making data public the way we are making data. So we're not going to be replaced, at least on the timescale of the next few years. But
Consider talking to the Astro Data Lab people. To the Astro Data Lab people, they're co-locating a lot of data sets.
I'm always happy. There's definitely opportunities I haven't explored.
That would be worth it.
Okay.
They have some pretty large storage facilities and the interface to actually support them.
Sure.
There are
A lot of things we do, we do things not. We are astronomers, so many things we do are not. They're good enough, but could be done better by other people for sure.
I'm not suggesting that the Sky Portal is a terrific system. So
No,
it's something to consider.
Yeah.
Maybe one more question? No more questions? No? Okay, well let's thank Chris again.
And please take these because I don't want to take them back. I'm not collecting them. All right, that's yours. That's mine.
Yeah, good talk, huh? Yeah.
Thanks. Very
Thank
good
you.
talk.
Thank you.
Yeah.
I think I went over to.
Not too bad. No, pretty
Oh no,
close.
not too bad. Okay.
Sorry.
I did see. Are those actual clogs? No,
I'm not sure.
I'm not sure. I got confused at some point, so I was.
Mm.
Well, thank you.
Thank you. Thanks for great
I'll head out.
Sure.
Hey, doggy.
That's your stuff.
Hi.
Yes.
No pressure.
I don't.
No pressure.
We've got some over here in the thing. Yeah, good talk.
Thank you.
We've had Ben Chappie give a talk, and Stanek was here years ago. But
Kochanek, yeah.
I'm sorry.
Yes.
Kochanek was here years
People
ago.
confused I would be confused too.
I'm not confused. It was
No,
just a
Chris
slip.
and Chris.
Yeah.
His name is also Polish, actually. He's really not Polish, but his name is Polish.
Nice. But yeah. So, have you considered, since you have big pixels, you could recover some sub-pixel information with just like drizzling